Okay, so we're going to be looking at this first question. I kind of kept it as the PDF from the College Board, so sorry that it looks different from what you guys have on the Google form. Again, I think I've said it before, but I wish I could push through the PDFs, but it just makes it harder to look at and see your answers. So it's just kind of easier to do it in the Google form. So with this, we're saying two students observed water flowing from left to right through the section of pipe shown above, which decreases in diameter and increases in elevation. The pipe ends on the right, where the water exits vertically. At point A, the water is known to have a speed of 0.50 meters per second and a pressure of 2 times 10 to the 5th pascals. The density of water is 1,000 kilograms per meter cubed. So before we start, this is kind of an example of one of our quantitative qualitative questions. It's asking us about a physical situation, and what we're doing is we're kind of talking about it in a qualitative way. We're saying, hey, what's right, what's wrong, and why? Talk about kind of qualitatively without equations, what physics backs up this idea. And then later on we get kind of more quantitative where we're actually doing the math behind it. But so it's one of our qualitative quantitative type questions because we're thinking about it qualitatively and then quantitatively, and we're kind of bridging the gap with some equations. But yeah, so it's one of our qualitative quantitative, one of the ones, the main one, the 60% worth one that we will see on the AP test. So a lot of it doesn't always follow this format where you have to say, oh, student X says this, student Y says this. But this is an example of one. This is a pretty common example of one where they're making claims and you're talking about the claims. So what I'm going to do, or what I already did, whenever I get one of these that has students making claims, I like to kind of section off each claim, because what they're going to ask us in part I, and IV4, I guess because it's the number, is they want us to say just what aspects are correct. So when they're saying what aspect is correct, we just can verbatim say what aspect is correct. We can just quote student Y and student Z. So in order to talk about their claims, the easiest way to do that is really to just go in there and say, hey, what claims are they making? So yes, if we read it, we say, student Y claims that the pressure at point B is greater than at point A because the water is moving faster at point B. So yes, technically they're making one claim, but we can split that into a bunch of little subclaims. In this case, I said, okay, well, this is really two statements. It's one claim, but two statements. There's two aspects that go into this statement. So it's not just the student making the whole claim, but the student saying the pressure at point B is greater than at point A is one aspect of that claim. And then the water is moving faster at point B. That's another aspect of this claim. So I like to section those off. I usually wouldn't have a highlighter. I would just kind of be like, whoop, and whoop. That is a claim. Then we're looking at student Z. Student Z claims the speed of water is less at point B than at point A because by conservation of energy, some of the water's kinetic energy has been converted to potential energy of the Earth water system. So this is kind of loaded. Yes, again, it's one claim, but there's really a few different statements that make up that subclaim, to make up that full claim. So in this case, the student's saying the speed of water is less at point B than at point A. That is something that we could check. That is an aspect of their claim. They say that they're using conservation of energy. That one is a little bit harder to identify. It is kind of an aspect of the claim. They're using it to support what they're saying. So we can write that down as an aspect about what they're arguing. And then some of the water's kinetic energy has been converted to potential energy. So that's another aspect of this claim. That's another statement that we could prove true or false. So indicate any aspects of student Y's claim that are correct. So if we're looking at this, the pressure at point B is greater than at point A. The water is moving faster at point B. So yeah, let's just kind of go in here and see if those would be right or not. So this isn't asking us to do the math. At this point, we shouldn't come in here and start doing all the math with Bernoulli's equation, but we have water that's flowing, so that tells us right away we have to look at pretty much our equations for flowing water. So we have to either use Bernoulli's or the continuity equation. We can't use that P equals rho GH. It's P naught. We can't use this equation because this is for stationary water. That's just for static systems. So this is flowing water, which means we have to look at this from either Bernoulli or we have to look at it from the continuity equation. So let's look at this first statement. The pressure at point B is greater than at point A. So we can set up our situation at point A and at point B. And again, we can set it up, but not with numbers. Let's just say PA plus rho G YA plus 1/2 rho VA squared has to equal PB plus rho G YB plus 1/2 rho VB squared. So we've set up our Bernoulli's equation. Again, we haven't fully set it up. We're not doing anything with it, but we can kind of start to get some ideas down. So it tells us, or we're kind of looking at this first. First, we can set up and say, well, point A is kind of at a height of 0. So let's just call this term 0. So we say PA plus rho G YB plus 1/2 rho VB squared. So if we're looking at this, the height, obviously, we have gained, Java update, great. We have this term now, right? We have a gravitational potential energy term at point B, which we did not have over there. So that means that either the pressure or the velocity would have to go down in accordance with this. We have to have this side, everything at point A, equal what we have at point B. So because we have this increase in gravitational potential energy, it means that we had to sacrifice something somewhere. We either had to sacrifice the velocity, the kinetic energy term, or we had to sacrifice the pressure term. But one of these has to decrease because we had to give some of the energy to gravitational potential energy. So there's no really way for us to check pressure without doing the math, but there is one way that we can check the kinetic energy term, and that's using our continuity equation, this idea that the volume flow rate is constant throughout the pipe and that the mass has to be conserved. So we can use this area of A, velocity of A, equals area of B, velocity at B equation. We can see and say, well, the area at A is larger than the area at B, which means the velocity at B is greater than the velocity at A. Right? If we're looking at this smaller area, which means that the velocity would have had to have gone up. So if we're looking at this, well, our velocity term over here, we have a pretty, I'm just going crazy with that, a small kinetic energy term, which means then we'd have to have a larger pressure term equals smaller pressure term because we had to sacrifice something, plus an existent gravitational potential energy term, let's say a larger kinetic energy term. So now if we're looking at this, we kind of have this qualitative idea of what's going on. Sure, we used an equation, but we didn't plug in any numbers. But we have this idea that the pressure at A has to be greater than the pressure at B, and the velocity at B has to be greater than the velocity at A. So now we can check our statement. So any aspects of student Y's claim that are correct. Student Y is saying the pressure at B is greater than the pressure at point A, but we said that that's not right. So this is not correct. Let's write no. But the water is moving faster at point B. So that one we did see was correct. So we said the water is moving faster at point B. So then if we're going to answer this question, the way that we have to answer it, so indicate any aspects of student Y's claim that are correct, the aspect that is correct is the water is moving faster at point B. So that is an aspect, and that's what is correct. And what's nice is that they're not asking us to justify it in any way. I don't know why I can't line this up nicely with the page. It's only in a weird square grid, but I will highlight it. So that's my answer for AI. The water is moving faster at point B. That is the aspect. That is the direct statement. That's all we have to do is just quote that. indicate any aspects of student Y's claims that are incorrect. Support your answer using physical principles. Well, we said the aspect that is incorrect from student Y is the pressure at point B is greater than that at point A. All right, and now, so yes, we've stated the aspects that is incorrect, but we have to talk about physical principles that make it incorrect. So we made our argument, we constructed our argument based on the Bernoulli's equation, which is really just a physical principle, a physical statement of conservation of energy. So we can say pressure at point B is greater than at point A. This is due to conservation of energy. The amount of energy at point A has to equal the amount of energy at point B. This is dictated by Bernoulli's equation for fluids. So we can say what we said before. Due to conservation of mass and the continuity equation, the velocity at point B is greater than the velocity of point B, than at point A. To satisfy conservation of energy, pressure at A must be greater than the pressure at point B. And then I may actually say, kind of link why we're talking about the velocity. This means that the kinetic energy at point A is less than the kinetic energy at point B. So that's a little bit long-winded, a little bit longer than we needed to be, but hey, we talked about our answer using physical principles of conservation of energy and conservation of mass. Okay, now going on to student Z. Indicate any aspects of student Z's claim that are correct. So let me just kind of partition this off. I don't know if that's the best way to do it, whatever. So any aspects of student Z's claim that are correct. So let's see. The speed of the water is less at point B than at point A. Let's see. And we said, no, that's not true. The speed at point B is greater than that at point A. So that's not right. Conservation of energy, the fact that they referenced it, that's correct. Let's make a little note of that. The fact that they're using conservation of energy, that's a correct aspect. And then some of the water's kinetic energy has been converted to potential energy of the Earth water system. So yeah, we can say that that's correct too. This idea that down here we have energy in the form of energy per volume in the form of pressure, and we have this kinetic energy per volume. And then at the end we have pressure at point B plus this gravitational potential energy per volume plus the kinetic energy per volume at point B. So yeah, we can say probably, I know a lot of it's coming from the pressure, but we can still say that there was this energy over on this point A, and that energy has transformed into another form of energy through pressure, potential energy, and kinetic. Yeah, we can say that that's reasonable. It's a little bit weird to say because we have less kinetic energy. That's being weird. We have less kinetic energy at point A than we do at point B, but we can think about energy as this whole, this large amount of this idea, this ability to do work. So we have that yes at point A, and this full pot of energy then can kind of choose where it's going, if that makes sense. We can kind of say, hey, we have it all in this form of energy, and we can put it however we want it. Yeah, so this idea is a little bit weird, but we can say that it is correct. So we can say student C is correct to say to use conservation of energy. And we can also say the aspect that's correct is sum of the water's kinetic energy has been converted to potential energy of the Earth's water system. So that is an answer for 3. Let's move down here. And then the fact that's incorrect. We said the speed of water is going to be greater at B than at point A. So indicate any aspects that are incorrect. Speed of the water is less at point B than at point A. This is incorrect due to conservation of mass and the continuity equation. The volume flow rate must be constant throughout a pipe to satisfy conservation of mass. The area at point A is greater than at point B, so the velocity at point B must be greater than at point A. All right, so that is us referencing a physical principle, the conservation of mass. All right, cool. So that is part A, a little bit lengthy. That is the longest part. So then calculate the following at point B, the speed of the water and then the pressure in the pipe. So for the speed of the water, we kind of already set up our equation for it, but we have this idea that A1 V1 has to equal A2 V2. So we know, or sorry, I can call this AA, VA, AB, and VB. So we can say, okay, at point A, we have a diameter of 2.5 centimeters. And if we have a diameter of 2.5 centimeters, then we have a radius of 1.25 centimeters, which means that our radius at point A is equal to 0.0125 meters. Our velocity at point A is equal to, what is it, 5? Where did I get that from? Oh, at point A, the water is known to have a speed of 0.5 meters per second. 0.5 meters per second. The radius at point B is, what is it, half? 1.5, so 0.75, so 0.0075 for the radius. 1, 2. And then the velocity is what we don't know. So we can set up the area of a circle is pi r squared. Pi r squared. We can cancel out pi, make life a little bit easier. And then we can solve that with our calculator. So we end up with a velocity of 1.388 meters per second. Okay, cool. And then we want to know the pressure in the pipe. So this is, again, just asking us to use Bernoulli's equation. So I'm not going to write out the whole thing because we talked about it over there, but pretty much we can cancel out the height term, the gravitational potential energy term for side A because it's at a height of 0. So we can, again, plug in what we know. So we know the pressure at A is 2 times 10 to the 5th pascals plus 1/2 times, so this has a density of 1,000 kilograms per meters cubed, and the velocity is 0.5 at A. Has to equal PB plus 1/2 times 1,000. We just said that the velocity at B is 1.388. plus 1,000 times 9.8, and then the height at B is, it is 5 meters above this middle point that we're calling point A. So it is a height of 5 meters above it. So we have a Y. If we're calling point A 0, then this has a height of 5 meters. All right, then when we plug that into our calculators, we get PB, pressure at point B, is equal to 150,161 times 10 to the 5th Pascal. Oh, wait, no, I don't know where I got that from. Pascals, which is the same as about 1.5 times 10 to the 5th Pascals. 1, 2, 3, 4, 5. Yep. All right, that's an A. Cool. So if we look at that, we predicted that the pressure would be less, and it is less than 2. So that's good. And then there we go. So for C, a valve to the left of point A now closes off that end of the pipe. The section of pipe shown is still full of water, but the water is no longer flowing. Calculate the absolute pressure at point A. This pressure that includes the effect of the atmosphere. All right, so what we're saying here is we close this off, and now our water is not flowing anymore. So now we're dealing with this non-moving, oops, got rid of what I didn't want to, that's okay. Now we're dealing with the stationary fluid. So we are saying at point A, what is the absolute pressure? So if we're looking at this, we're saying, okay, the water is filled up to here. And one of the main things that we talked about when we talked about stationary fluids and their pressure is that at the same depth, the pressure is going to be the same anywhere at that depth. So it doesn't matter that it's all the way over here at this end. All that matters is that it is a depth of 6 meters below the surface. So its depth is 6 meters. We have 5 plus the 1. So it doesn't matter that it's here. It is still 6 meters below our surface. So we can use our equation that says the pressure is equal to P naught plus rho G times the depth pressure. So we're looking at absolute pressure, which means we're going to include 1.0 times 10 to the 5th pascals for atmospheric pressure, plus 1,000 times 9.8 times the depth of 6 meters. So when we plug that in, 185, we get a pressure of 1,58800 pascals. Cool. And then finally, the last little point, yours looks a little bit different, so I'm sorry about that, but we're saying, hey, there's a bubble in there. What forces are acting in the bubble? We know that bubbles are going to rise up when we put them under the water. And when we are underwater, we have a buoyant force and a gravitational force. Yes, it's a bubble, it's filled with air, but air still has mass. So we still have the gravitational force, but we know that there's a buoyant force acting upwards on the bubble. So yeah, that is that question. I'll just kind of show the key. I'm not going to go over it because we kind of just did that. But if you want to look through the key, you can just kind of pause it here. And then the second page, feel free to pause it and give it a look if you so desire. All right, but yeah, that is that question. Yeah, hopefully that was okay for one of our qualitative questions.